Check it out now, y'all.
nanoHUB-U, online instruction.
Welcome to Module 1.3. As you may recall, in the last module, I tried to explain how you could start from a differential equation, the usual form of the Schrodinger equation, which is E times a wave function psi is this differential operator times the wave function psi, or acting on the wave function psi. You could start from something like this and then expand your wave function in terms of a known set of functions. These U's are what are called basis functions, and these are functions you know, nothing to find out about them. You know what they are. You've chosen a particular set. And you expand this wave function as a linear combination of those things. And what you don't know are these coefficients. So what was an unknown function then becomes a set of unknown coefficients, okay, which you could write in the form of a column vector. So you could have psi1, psi2, psi3, etc. And the length of the column vector would depend on how many basis functions you use to represent your wave function. And once you do that, then in principle, this differential equation can be turned into a matrix equation that I've shown here, that you go from this to a different matrix equation with H, what was the differential operator here, is now a matrix here. You see, it's now a matrix, the differential operator. And as I explained in the last module, that there is a well-defined prescription. That is, if I know the basis function, if I know this differential operator, how I can write down the elements of that matrix. And when people use a first principles method, that is what they would normally use. That is what they would. And on the other hand, in this course, what we'll be talking about, we won't be talking about this first principles method, because as you know, in this course, it is really more about current flow. And as you know, this current flow involves the H and then this connection to the contacts and this all non-equilibrium aspects that we really want to talk about starting next week. And in this week, what I'm trying to do is describe to a relatively simple models for H that we can use for all the problems we want to talk about. Now, but the method we'll talk about, however, is perfectly general. So if you wanted to use a more sophisticated form for the H, that's fine. The rest of the method applies to any H. Anyway, so the point is that in first principles methods, you'd start from this operator and directly find those elements, whereas in these semi-empirical methods that we'll talk about, one writes down this matrix by making sure that the results match well-known results, either from theory and or experiment. So there are things that people agree on for a particular material that are known from earlier work, from experiment and theory, and what you want to make sure is that this matrix that you use matches all that. And once you have adjusted your matrix to do that, then you can go ahead and do other problems, the non-equilibrium problems we want to talk about, starting from there. So what I want to explain in this module, to start with, is one way one can write down this matrix so as to fit well-known results. Now, the result that often one could use is, one thing, this is one of the early insights in solid-state physics. That is, that electrons in a solid, as in a solid is a complicated object, and an electron going through a solid seems like a very complex thing. But one of the early insights of solid-state physics is that an electron in a solid behaves almost as if it's in vacuum, but with a different mass. So when you have a Schrodinger equation like this, that's of course for electron in a vacuum, and then this potential would represent the solid. What that would mean is that potential is a very complicated thing. It represents all the atomic potentials that the electron sees. But what you could do is, you could replace this with what is, so this is what you call Schrodinger equation, and you could replace it with what you might call an effective mass equation, which looks just like this, which is why often people forget the difference. They still call it Schrodinger equation. But it's really an effective mass equation, where this mass is not the free electron mass, which is a standard fundamental constant, but it is something that is different for different solids. So if you're doing it for a metal, it will be one thing. If it's gallium arsenide, it will be something else. If it's silicon, it's something else. Use the right mass there. Now, what makes it simple relatively is that then the potential term that you see here, that's no longer the atomic potential, because the effect of the entire periodic solid has all been subsumed in the definition of that mass. So after that, whatever potential you see in the effective mass equation, which formally looks just like a Schrodinger equation, but whatever potential appears there is not this atomic thing anymore, but what is on top of it. So all the man-made potentials or impurities, defects, things beyond your actual solid periodic lattice. All the extra stuff is what goes there. See? And this is a description that has been widely used for over 50 years now to describe electrons in solids. And so let us say we start from something like that. We use that as a reference. And what I'll do is look in this problem at a simple one-dimensional example. In the subsequent modules this week, we'll talk about 2 dimensions and other issues. But right now, let's do a very simple one-dimensional example. So this is, let's say, d2, dz2. And note that this m appearing here is now the effective mass, not the free electron mass. And we are really dealing with the effective mass equation. And so the question is, I want to replace this with a matrix equation looking like this. And how should I choose the parameters of this matrix so that this and this give me the same results that are comparable, right? Because after all, this equation with the effective mass, that has been verified, checked against experiment with many experiments and theory, and people believe this to describe electrons in a particular solid. So that I'm taking for granted, given what is known about that material. And then I'm trying to adjust the matrix so that the 2 things match. Question is, how will I go about matching them? Okay. Now here, this is where what one could use is this dispersion relation idea. That is, you see, in general, I guess this is now u of z. In general, when you look at this equation, I can't write down a solution till you give me what is u of c. What is this potential? But I could write it down very easily if I simply assume this u of z to be some constant. So u0. So if I assume that it is some constant, u0, then as I mentioned before, anytime you have a differential equation with constant coefficients, you can just write down the solution as, sines and cosines or exponentials, and it's straightforward. You see? That will always satisfy that equation. So for example, if I just write here e to the power I k z, if I put here e to the power I k z, then the second derivative means multiplying with ik twice. So what you get here then is minus h bar square over 2m like you had, and then taking 2 derivatives is like multiplying with ik twice, plus u0. So, as I said earlier, with differential equations, it's not like I can logically tell you how I thought of this particular solution. But what I can show you is that if I assume that, then it fits. It satisfies that equation. So, offhand, if you have never seen an equation, you may not know how to write down a solution. But if someone claims they have a solution, you should be able to, in a few minutes, say whether he's saying the right thing. You can check easily. So anyway, so the point here was differential equation with constant coefficients, solutions can be written in the form of exponentials. Okay, so you put that in, and we have e to the power ikz, we can cancel that, and that gives me what you'd call the dispersion relation for this differential equation. Okay. In fact, the way it often works is that people know from experiments that the energy is related to the k, or actually this h bar k is like momentum. So often this also could be written as p squared over 2m plus u0. You can often write it this way. So often what is known experimentally is this energy ek relation, or this energy momentum relation. And once you know this, you could kind of work backwards and figure out the kind of effective mass equation that would actually give you that. So you can, given an equation, you can get to the dispersion relation, or if you know this from various measurements, etc., then from here you could work backwards and write down a differential equation that does this. And then what you could do is use this equation to handle all kinds of problems that do not admit a dispersion relation, in the sense that, let's say I now want to describe how electrons behave when this potential is varying with distance, when you have a u of z. Okay, I can start from here, this equation, and then make the u z dependent. But to start with, what you do is you can adjust parameters so that it describes the homogeneous material well, correctly. That is like at least a necessary condition. What may not be obvious is whether that's a sufficient condition. Okay. Anyway, so given this, next question is, how do I do the same with my matrix equation? And the idea again is that if you had a matrix, if you have some set of equations that describe a homogeneous material, then the current solutions can be written in the form of exponentials, and the ek relation, this dispersion relation that you get, that should match whatever you'd get from the corresponding effective mass equation. So those two things need to match. Okay. So let me now try to explain what this matrix equation would look like. And here we are talking about this simple nearest neighbor tight binding model. So it is conceptually, it's like basis functions are like a particular wave function, a particular basis function is localized around one atom of this. So this atom or that atom, these are kind of what the basis functions look like. And what these psi's, the psi1, psi2, etc., represent is, like if you think of the wave function as a linear combination of these, then those are the coefficients. Okay. So now if I write this out, the full thing, psi1, psi2, up to psi n. So lots of them, like n of these points. And then if I write the h here, that's the matrix, and then you have the psi again. And what does this matrix look like? Well, this is a nearest neighbor tight binding model. What that means is you only have non-zero elements on the diagonal, or on the upper diagonal, or on the lower diagonal. Why is that? Well, because when I try to write this equation in terms of its components, I could take a particular row, let's say psi n, and write it out. It would look like E psi n is equal to, actually let me write, say, E just psi 2. Instead of writing a general one, let's just write the second row. So what you'd get is this thing times that, this thing times that, the next one times that, and so on. So it would look like, if you wrote down E psi 2, it would look like the first one, that is H12 times psi 1, I'm sorry, H21, 21 times psi 1, plus H22 times psi 2, plus H23 times psi 3, etc. And nearest neighbor tight binding model, nearest neighbor models mean that only non-zero elements are those for which these two indices differ by less than 1. So 2, 2 is fine, 2, 3 is fine, 2, 1 is fine, but 2, 4 is 0. So after that, it's all zeros. So what that means is if you go back to this matrix, you go to any row, there will be these 3 elements there, which are non-zero, wherever you go. And the rest are all zeros. So this is all zeros here. Okay. Now, because we are talking about a homogeneous solid, remember that's the case where we want to compare dispersion relations, every row must look the same. So it's like E psi 2, that means I'm looking at the point 2, and I have something, there's a diagonal term, and then there's a coupling to the left and a coupling to the right. And I move to another point, say the third point, now I have a coupling to the right, coupling to the left, and a diagonal term. So there's always these 3 things. And since it's a homogeneous solid, it doesn't matter if I'm here or there or wherever. They must all be the same. So what that means is, if I looked at the diagonal elements, they must all be a particular number. Let's say I'll call it epsilon. So all diagonal elements are the same. Similarly, all the upper diagonal elements, those are like from here to there or there to there, again must remain the same. So let me call that, say, T. This is T, that's T, that's T, that's T, etc. And these matrices are usually Hermitian. And that ensures that when you find the eigenvalues, it's always real with Hermitian matrices. And Hermitian means that this matrix must be equal to its conjugate transpose. That means anything on the diagonal must be real, and anything here must be like the conjugate of what's here. Anything here is the conjugate of that one. So, and assuming for the moment these are real things, then if those are T's, these should also be T's. So in a model like this, you see, when I'm representing a homogeneous material, the point is I basically have 2 unknowns, 2 parameters I can play with, an epsilon and a T. And the question is, how do I adjust those so that the dispersion relation for a homogeneous material looks close to what I believe it to be correct from experiment and theory, from various things. Okay. So what I now want to explain is how you'd find a dispersion relation from here. So this is where, if you wrote down one of these equations, so let's say I go to the nth line here, psi n, so you could write it as something like this. E psi n is equal to, there will be a T connecting to n minus 1, epsilon connecting to n, and a T connecting to n plus 1. So you'd have something looking like this. So if I put n equals 1, I'll get one equation, n equals 2, n equals 3, n equals 4, and that's how we get all the equations one by one. Okay? And now the point is that you can write down the solution to this entire set of algebraic equations in the form of an exponential. You see, and what allows me to do that, of course, is because every line is the same. If it was not a homogeneous thing, so this line was like epsilon 1, T1, etc. This line had to do with T2. So if it was changing, then I couldn't have done that. But because every line is the same, I can do just that and write psi n as psi 0 e to the power I k n a. Na is like this is kind of like the location in Z. That is, if this axis, if you call it Z, then the location of the nth point is like n times a, where a is this distance, the distance between points. So that's what we write as e to the power I k n a. Now, if I assume this solution and substitute it back in there, what I can do is, I guess the easiest way would be, let me divide through by psi n. So I can write it as E is equal to T psi n minus 1 divided by psi n plus epsilon plus T psi n plus 1 divided by psi n. So all I did was started from this equation, just divide it through by psi n. And what you can check is, if you assume this solution, then what is psi n minus 1? Well, it is psi 0 e to the power I k n minus 1 times a. Whereas psi n is psi 0 e to the power I k n times a. And so, when I divide psi n minus 1 by psi n, see, everything cancels except for this e to the power minus I k a. So this gives you e to the power minus I k a. Similarly, if I did psi n plus 1 divided by psi n, I'd have got e to the power plus I k a. So if I use this, then what you get is, and this is really like e to the power minus I k a, and that quantity is really like e to the power plus I k a. So I now have a ek relationship. Just like I did with the differential equation. We put in an exponential, and then you got an ek relation. And as long as that was satisfied, the original solution would work. Here also, this solution will work, provided E and K are related this way. So that gives me then a relationship between E and K, which will look like this. E is equal to epsilon plus T e to the power minus I k a plus T e to the power plus I k a. And these two exponentials I can combine to get a cosine function. And this would be the EK relationship for our choice, for a particular choice of parameters, epsilon and T. And this is what we would want to compare with what we had obtained for the differential equation. So just let me take all this. So in the differential equation, you had these two constants, an m and a u0. And we obtained this relation. The question is, how do we compare those two things? Because one looks like a parabola, the other looks like a cosine function. Okay? Now, if we plot them, usually the way they would correspond would something like this. You see, E versus K. If you plot for this one, it's like at K equals 0, E is equal to U0. Whatever that is, and then it increases parabolically. Actually, usually in solids, this bottom of the band, that's what's called the conduction band edge, and people usually write that as E sub C. So that's kind of, the notation I'll use from here on. So instead of this U0, which was this constant potential energy that I put in, which is why we wrote it as U0, let's write that as just E sub C. And that's a constant, we're just calling it that because that's the standard way of referring to the bottom of the conduction band. And this parabola, that's what this mass determines. On the other hand, if you were plotting this cosine function here, it could look something more like this. Cosines, as you know, kind of go on like that. And the point is that right around here, if you chose your parameters carefully, they could match very well. And one of the points I've made in the first part of this course, part 1, is that when it comes to current flow properties, what matters is the electrons right around the electrochemical potential. That is, usually a solid in equilibrium, there's an electrochemical potential that tells you how far the states are occupied. And what matters is the EK relation of the electrons right around there, over a range of a few kT plus the applied voltage. And so, if you're trying to model electrons, what you try to do is make sure that over that range, you describe the EK relation quite well. The fact that it doesn't match here is not of great importance as long as these do not conduct. And in any case, usually this effective mass equation itself is not exact either. I mean, the real thing might actually look more like this anyway. In other words, the effective mass was probably an approximation to something that looked this way anyway. See? So there's no particular reason to try to match that parabola exactly over wide ranges of energies. Now, if you're trying to match this right around here, question is, how will I choose my parameters here? And that is where, let's go back to this cosine. What you use is this, I guess you'd call it a Taylor series expansion, which is that cosine of x for small x can be written as 1 minus half x squared. This is of course not exact, but for small x, it describes the cosine function quite well. Okay. Now if you use that, then what you get is, instead of this cosine Ka, then, what I get is 1 minus k squared a squared divided by 2. So, that gives me, let me write it up here, E equal to epsilon plus 2t minus 2t times k squared a squared divided by 2. Okay. This is it. Now, this is then the approximate dispersion relation for this matrix equation. And what we want it to do is look like, we want it to make it look like EC plus h bar square over 2m times k square. Where m is this effective mass that matches experiment well and so on. So this is what we want to match that. And so you can see immediately what you should do is choose your epsilon and t such that this sum fits that, is equal to EC, and this quantity is that. Now one point to note is that the t should be negative in order to match this. And this you can kind of see why. You see, I said that this cosine function looks like this, but if you think about it, what we're writing is this epsilon plus 2t cosine Ka. And at k equals 0, the cosine of 0 is 1. So at k equals 0, this quantity is epsilon plus 2t. Whereas the way I have written it is like the minimum. What I mean is, if t were positive, this curve would have looked more like this. Because it would be epsilon plus 2t out here, and when ka is equal to pi, that's where it would be epsilon minus 2t. But because t is negative, that's why this actually is here. It's epsilon plus 2t is actually less than epsilon. It's here. And epsilon minus 2t is actually more than epsilon. It's there. So the point is that usually then, when you're describing bands of this type, the t would be a negative number.